and he is a fellow of the IEEE. You know, we've got a lot of people like that here in this room this week. Please take a chance to reach out and connect with them, and we'll ensure that you stay a part of the family as this conference continues and afterwards. Bob?
Thank you for that long introduction. I'm also become sympathetic with the previous speaker. As I walked up to here, I could no longer hear the introduction. It is very strange, the acoustics here, that as you're standing up here, you cannot hear the speakers. So it is an anomaly of this particular room. I want to thank you for being here today. I'm part of the IEEE, being the first IEEE speaker, and having listened to the previous two speakers, I feared that I was going to be constrained to painting in their picture because I have very little to disagree with. I do want to say that although it's not on my slides, the new thing I want to emphasize after listening is the fact that the technologies that are going to make this field succeed 10 years from now are probably going to be invented in lots of different places, under lots of different technical areas, and have to be integrated. So you're not going to have an intelligent transportation system that develops its own technologies. It's going to be a net importer of technology, and we're trying very hard to make that happen. I'm old enough to believe what I just said. I was in the U.S. government back in the early 90s when an intelligent highway system was proposed and a new program was developed. And the image that we had of the technical possibilities at that time was minuscule compared to the technology we have today. And it wasn't because that program developed new technologies. It was because we had advances in telecommunications, in computing, in semiconductors, and in 1,000 other fields that made the whole system much better, much more attractive today than it was then, and is going to make it more attractive in the future. I like to show this slide, not because I think this audience needs it, but because I like this slide. And it shows a change that we have seen. If you look across the bottom, on the chart nearest to me, you will see, if you lifted the hood of the 1965 Ford Mustang, you would see the air cleaner, the carburetor below it. This was an engine I learned to work on. I could work on that engine. By the time you got to the 2012 Ford Mustang GT, you had this wonderful, almost sealed package that is what it's going to be. The electronics ran it. If you want to know what's wrong with it, you plug the computer in, it will tell you. There was very little that I could fix by the time I got to that. Now we're to Tesla, and then you open the hood and there's nothing there. It's just another trunk. The technology is changing dramatically. It's shown by opening the hood. This I find is a very effective slide to show people who were alive in 1965. Because they have lived through this change from an automobile being a mechanical device that ran off exploding gasoline to basically a computer on wheels, an electrical device, a transportation device, not a mechanical device. So the change is there, the change is ongoing. The vision that the IEEE has in this area is to provide transportation that works for people and the planet. And as you've heard by both the previous speakers, safety is a critical issue. One of the anecdotes we had at one of our conferences is one that I'm going to repeat because I liked it so well. Because we are trying to actually retain some of the safety features we've given away by going to automobiles. We know today that if you decide to go out and have too much to drink and get into your automobile, you can slam into a concrete bridge and kill yourself. When we had a horse and buggy, the horse was too smart for that. We actually had a vehicle that shared the intelligence with the driver, so you couldn't kill yourself by running high speed into a barrier because the horse would say, "I'm not going to do that." Well, now we're going to have a car that says, "I'm not going to do that." So we're not really getting to a new world where we have like smarter transportation. We're actually taking the idea of smart transportation we had for a long time ago and bringing it back in. Let's give some of that intelligence back to the vehicle. And the other thing that we're changing, the other part of that vision that's critical, is to look at transportation as a service. For years and years, at least in the United States, we have been trained to look at transportation as buying a car. And the previous speaker talked about the number of cars per people and the dream of owning a car. We probably ought to change, well, not probably, we need to change the world to think not of buying a car, but of buying transportation, of having transportation, not of having a car. I think the whole world is going to be better when the whole world starts thinking of buying transportation. At one of our previous conferences, a representative from Volkswagen painted a very beautiful picture of a family out at a park, and they, when it was time to go home, the father picked out his cell phone and said, "We need a car in 5 minutes to go home from the park." Put it back in his pocket, and they walked down to the street. The car drove up, and they got in. They didn't own the car; they only wanted the transportation. They don't care what car it is. So I think when we get to that world, the world that Volkswagen says we're going to get to, whereas transportation is a service, not a status symbol or a luxury item that we think we want to have, then I think we will have succeeded in what we're trying to do. We do have a fundamental constraint, and this also has been brought out by previous speakers, that the change in transportation is going to be, always will be, slower than it was in semiconductors and telecommunications. This is because the individual investment is high. If you talk about automobiles, I have a huge investment in automobiles. It's the only way I can get transportation to the city in which I live. I don't turn those over very rapidly. So the cost of changing that infrastructure is very high. In fact, I was amazed that one of our graduate students was doing a study for us and came across the fact that in the United States, just to change from leaded gasoline to unleaded gasoline took about 12 years and cost more than $1 billion. So if you're talking about a change more fundamental than taking an additive out of gasoline, you have to think long-term, high cost. The infrastructure is there. We're counting on a lot of things that are there, and the turnover is going to be slow. And the other side part of that is that you also have to get the infrastructure investment payback. As part of public policy, people are going to insist that if they allow this infrastructure to be built, assuming it's going to be paid back over 10 years, they're not going to allow a policy that says, no, you can't have it. We're going to take that money away from you and send it somewhere else. So there's going to be political pressures to make sure that the transition is slow. This brings an interesting challenge to those who are trying to develop the intelligent transportation system, because technology is going to change much faster than that. The system you're designing today probably won't get into the market for another decade, and the technology underpinning your system is going to change in a decade. So the challenge that I face, that you face, that we all face, is how do we make technology that makes the system better and get enough return on investment so that we can keep it alive and keep it refreshed until it can make it into the system and make it big time. One of the examples you heard earlier was let's do aftermarket things, or let's do small fleet studies, or let's do a variety of things. But it's going to take our creativity to understand how to take this technology and get us where we need to be as the various nations you live in and as a world. Now I want to talk just a minute about technology, policy, and standards. As you heard from the extended bio that I had there, I did work for many years, nearly 30 years, at the National Institute of Standards and Technology. So I grew up in the standards field, and being in Washington and working in the Office of Management and Budget, I was immersed pretty heavily in science policy. If you notice, the name of the organization was the National Institute of Standards and Technology. We recognized and kept emphasizing that the technology is a critical thing. After that, standards and policy can put into place if you understand the technology. So what we'd like as an ideal is to have a broad enough technology base so you can develop the standards you need, so you can develop the policy you need, so that the whole thing works perfectly. But that usually, we usually don't live in that ideal of a world because of a lot of factors. What really happens, and very commonly, is the one on the other side, where the pyramid's upside down, where we're developing the technology as fast as we can, but because we have to have two different companies interface with each other, we've got to develop the standards quickly. And because this is such a wonderful idea, every politician wants to name on it, we have to develop a policy faster than that. Now, if in that situation we can succeed, but what it requires is the system be a lot smarter. If you notice, the inverted pyramid is stable, provided you keep building over its center of gravity. So that means everybody building the technology, the standards, and the policy have to be smart enough to not crash the pyramid. Usually we're not, and usually we crash the pyramid, and we do that. It means we're costing a lot more money and taking a lot more time to get the technology in place than it would have been had we been able to do it in a better and more stable way. So my point here is that all of these things are important, but if you do if you do it before you get all the technology, it's very likely that you're going to just restrain the development of this. If you standardize before you faster than you develop technology, you're probably going to constrain the development of technology. You get a less than ideal system. And if you develop policies, you can end up freezing technology development for years in an area which is too expensive. And I should give an example of that in the next chart. Because I want to talk here that technology actually has a very limited window of opportunity. I shouldn't say very limited. Time is arbitrary on that axis. But the point that I want to make here, let me first explain the chart, then I'll make the point. The chart shows 3 different technologies, starting at some time 0. We have 3 new bright ideas that are all going to take off. What you see is that each of them can be developed, but over a given amount of time that they're in a related field, they start overlapping with each other. Technology 1 starts taking from market from technology 2, and vice versa. After enough time, all of them can probably solve a lot of the same sorts of problems. So you have a limited time window to get your technology into the marketplace. Everybody talks about the window of opportunity closing, and I never really understood what that was until I had some studies commissioned by economists. And what I did is I had them look at the projects that we were going to start. And when they did that, they took the data, I asked them what was going to be the return on investment. And they told me, well, we should be able to get about 100 to 1,000 times more money back to the economy than we put in. Then I had a group of economists look at the projects we had completed. And they said, well, you've got about a factor of 4 to about a factor of 10 back. Why do we have a factor of 4 to 10 when we look backwards, and a factor of 100 to 1,000 when we look forward? The reason is each of them were looking only in one of the triangles, and they assume they can capture everything going forward forever to get a factor of 1,000. The fact of the matter is, other people are also trying to take away your technology space and making a difference. So you have to be careful on how this technology is going to develop. How does this relate back to where we are? Well, just think about what happened in the United States. We made a wonderful invention. Well, we didn't make the invention made worldwide, but in our country, Alexander Graham Bell invented the telephone. And we put a telephone system. So we now have we then wired the entire country to put wires everywhere so that we could have wonderful telephones. We then invented television. Hey, in television school, it's like radio with pictures. So we'll broadcast it over the air. So, okay, now everybody wants a telephone that has a wire, and a television which is wireless. Guess what, folks? Our telephones don't have wires anymore. We're running cables to every house. We blew it on the technology policy. If we'd have been really smart in 1900, we'd have said all telephones have to be wireless. And we invented television. We say they don't have to come on cable. We'd have saved billions of dollars in decades in work in fixing that technology change. Now that one, I don't think anyone would have been smart enough to ever figure out. But I like to use it because it shows that if we make the wrong policy decisions, we can end up costing ourselves a fortune. And that's a very important thing we all need to keep in mind. And the way we get to what I can do as a technologist is I can say, I can try to run faster and get all of these technologies more mature as fast as I can so that it's easier for people to make the right decisions. Okay, now let me give you some of the technology examples. I said that I'm going to emphasize technologies that aren't traffic technologies. There are other technologies under development which I think are going to make a huge difference in this field. One is wide bandgap semiconductors, where the world is developing wide bandgap semiconductors. When I was in Europe, I heard about the semiconductor industry teaming with the automotive industry. At the University of Texas, Austin, I hear about it. We're working on doing exactly the same thing. In Asia, they're doing the same thing. And the reason is the wide bandgap semiconductors are a game changer. They provide a margin for the other components. And to provide a very good example of that, in my research center, in my own personal research, we were brought into a project in Asia because they had developed this wonderful electric vehicle. And the problem was, the only problem they had with this wonderful electric vehicle is when you got to the end of the design, there was no motor in the world that could do what they wanted. And the critical reason why not is they basically used up all their cooling capacity for the power electronics. And therefore they needed a motor that could run at higher temperature than any motor could. Fortunately, we were able to find a set of materials that could do it. But what we're doing now is eating all of our margin in cooling semiconductors. If we can get to temperatures that semiconductors that inherently work at higher temperatures, we get better reliability, we can provide new capabilities we haven't thought of yet. We are already working on new system architectures. I know that we have programs for things like trains and ships, where we take the electric system and using these new semiconductors, you develop better performance already. And it develops new classes of materials, because not just the semiconductors. Well, you develop a semiconductor to work at high temperature, but then it has to go in a package. And none of those packages work well at high temperature either. So you've got a lot of material science work. But at the end of the day, what you're going to end up with is a transportation system with electronics that are faster and more reliable than those that we have today. The other issue that we have is that of situational awareness. I like to use the picture of the gas gauge because we've had so much exposure to internal combustion engines that as far as fuel goes, that's a little situational awareness we need. Take a look at the dial, that's what we need to know. For transportation systems, we actually have developed algorithms for bus companies to know the range versus the traffic level, the weather, and the terrain. So they will know if their bus has enough charge in its battery to be able to use on that route in the afternoon, or if they're going to have to reroute it for the afternoon because they don't have to, it will not survive given the way it was used in the morning. So we're starting to get that kind of information, which is a whole lot more sophisticated than the dial. Sensors are absolutely critical. I have to brag about the sensors that I happen to like the most, because they're training me to believe my vehicle rather than what I see. My car, the new car I just bought, has cameras that when I pull into a parking place, shows me the little white lines on the pavement on both sides. You may not think that's important, but if you happen to live at the University of Texas at Austin, we have parking Nazis that come in, and if your tire is on the slightest bit on the white line, you get a ticket. They need the money. And so everybody has to get out and walk around their car to make sure that they're not touching any of the lines. Well, fortunately, my car has little cameras. I don't have to get out. I can say, oh, yep, I'm fine. I just get out and leave. So it has saved me parking tickets by having that sensor. What it's also doing is going to make me a lot more comfortable when the car parks itself. Because now I know it knows where it is. Now it just depends upon me to make sure that I stay in the middle, and it can stay in the middle all by itself. So one of these, the situational awareness is absolutely critical. Propulsion energy. There's a number of issues that we can talk all day on how you get energy propulsion. Let's get an electric vehicle, but I'm not going to talk all day. There's a couple things I want to talk about though, and one is working with the utility. We talk about communicating with vehicles, we talk about communicating with traffic management systems. An interesting thing that we've run across working with a bus company in California is communicating with the utility. Let's set up rapid chargers and let's tell the utility when we're going to need a little power for the next 3 or 4 or 5 minutes, and let them do some dynamic reconfiguration of their own, and let them give us a special deal because we can communicate clearly and unambiguously when we're going to need the additional power. And so it changes the whole rate. It changes the whole dull interaction between electricity companies and consumers, where you just plugged in and took whatever you wanted, and they charged you an exorbitant rate for taking too much at a time when they weren't ready for it. Here you're talking all the time. You're not ever talking. Your computer's talking to their computer, and between the two, the bus system computer and the utility computer, you can work out something that works for everybody. The other thing that we're looking at is as we look at alternatives to fossil fuels, we're doing, as you see in the picture, is showing some work on comparing, does rapid charge work better, or does it work better to carry a fuel cell to charge your vehicle? And how do you make that? And because even if I go to natural gas, I'm going to need electric power because I'm going to have this connected vehicle that connects to everything. It's got to have enough power to communicate, to sense, to do all those things. So it's going to be an electric vehicle no matter how you go, what sort of propulsion you choose to use. So you've got to figure out how electric you're going to make it, where you're going to make it electric, You have the same things on ships. Do you want to make it all electric, or do you want to make it partially electric? You have the same things on airplanes, a more electric airplane. When do you stick propulsion in the mix? Those are questions that are going to be solved dynamically, but they're going to have to be solved. Signal processing. I think signal processing is an interesting area that is probably going to be solved. I just want to bring this one up because I think it's going to be solved outside this community, for this community, because the signal processing world is talking about a lot of applications in which you have time constraints. You got to get the answer in time shorter than something happens in the real world. They also have the fail-safe. They also are doing signal processing in areas where if you don't get the right answer, you kill somebody. And so signal processing has a lot of emphasis in those two areas. And so the signal processing community is developing tools which are going to be very important for this community. The other question that I find fascinating and was touched on here by both earlier speakers is the balance between the local control and large-scale control. Do I let every vehicle talk to every other vehicle in this environment and just everybody go and we'll do swarm optimization? Or do I still have the big brother in the cloud that is overseeing everything? And obviously, for the next 20 years, we're going to have a combination of both of those. Both of them need reliable communications. If you can't talk to the rest of the world and you're counting on it, we're in real trouble. For the large-scale system, big data is coming in over and over again. Latency is the critical problem with control of large-scale systems. To let you know, you're not the only ones who have that problem. If you look at the electric grid, a critical problem with the electric grid is the latency of telecommunications are too slow. The latency of getting data and analyzing the data makes it impossible to control the grid in time shorter than seconds. And in time shorter than seconds, really bad things can happen. Well, as your transportation system grows to look like the utility system, what that means is the latency of telecommunications is making it less and less possible for you to control the whole thing centrally. You need the autonomous control. So there's a latency, a technological latency limit that is going to drive what we can do in the near term. On the local thing, the other interesting aspect that we have to develop is we have to develop trust. And we develop trust, as you drive, if you think about it, you develop trust in other drivers. You watch how they drive and you say, okay, I know what he or she is going to do. I've been there, I've done that. I learned to trust the situation around me. How can I communicate electronically and be confident that, and my vehicle be confident that 2 vehicles over isn't broken? How do I develop that? How do I quickly get that intuition that this is a driver I trust or this is a driver I don't trust? I mean, right now we're doing studies in agents in various surveying areas where you're taking data that's an hour, that's a few minutes older than other data, and it disagrees. Is it because the situation changed or because you have errors in the data? That's a huge, big-scale problem that we have, and it's going to come, as we start going to local control, it's going to be a huge problem. We have to understand how to solve both analytically and possibly with driver in the loop. And the last one that's been mentioned a lot is cybersecurity, and there's 2 anecdotes I want to give about that, because they both have to do with my university. Some of you may have heard on the news about one of my colleagues who has made a career of spoofing GPS. And therefore he can take an airplane and have it land anywhere he wants to, because he can make it convinced that it went to where it said it was going to go. But he had to go somewhere else. He just recently did the same thing with the ship. Went the ship out in the ocean, spoofed GPS, and the ship ended up somewhere where it did hundreds of miles from where it thought it was, because he could spoof GPS. Now, if you do the GPS of my guidance system in my car today, I will look out the window and say, nope, you got that wrong. But if you spoof the GPS in an autonomous system, you can make the car go anywhere you want it to. So we know that those sorts of things exist, and we have to figure out somehow to develop ways of mitigating against them. The other one that we found very fascinating, is there was this mention of privacy, and I'm going to come back to it a little later. But some people, although you say if you've used the statement earlier was if you've used a cell phone, you've given up on privacy. But the fact is, we did a study at the university on a major highway going by the university, and about 1 out of every 100 cars had a jammer in it. So people couldn't follow them on their cell phones. Well, if you start counting on cars being able to communicate with each other, and 1% of them have jammers, what's that going to do to traffic control? That's an interesting cybersecurity question by itself. have the social implications of this new technology. The liability was mentioned earlier. I agree with everything that was said there, and I'm not even going to say anything different about that. Privacy, I just talked about, that privacy is important to some people, and people will take extraordinary measures to maintain their own privacy. And if you assume that they're not, if you build a system assuming that they're not, you're in real trouble. The other one that we're kicking around a lot in our meetings lately is this: is that if you start going with these wonderfully more automated systems, they make great tools for terrorism. Right now, we have to recruit a terrorist to drive a truck bomb into a building. What we could do then, if we can come up with a nice autonomous vehicle, we can control it to drive into the building and no one has to get hurt. I mean, it's a wonderful way to deliver pizza, and it's also a wonderful way to deliver explosives. So we have to understand how my autonomous vehicle is going to know the difference between pizza and explosives, and how my road is going to know the difference, and how the other cars are going to know the difference. Okay. Now, having said all of that, but if you noted, you may have noticed my subtle little statement on the bottom of each of these technology slides that says the IEEE is here. What did I mean by the IEEE is here? What I meant is that those are all the areas I talked about are all areas in which the IEEE is empowering and supporting and protecting communities that advance and apply the technology. The IEEE is trying to bring together a group that consists of the researchers who are moving this technology forward, the innovators who are turning the advanced technology into products, the practitioners who learn how to manufacture those products, how to install those products, how to maintain those products, and the educators who provide the skill set to take this advanced technology, make the next level of advancement in technology, and support the technology that we have. That whole community has to be healthy and working together for this whole, for the field to succeed. And that's what we are trying to make happen. That's the IEEE role in this area, is to bring together the communities, the diverse sets of people that need to interact, that need to talk, that need to work, give them the papers they need, the conferences they need, the meetings they need, the standards they need, the infrastructure they need to succeed. So in summary, we all know that the transportation is becoming more electric, more connected, and more autonomous. And I think that it's inevitable that some of that is going to happen. The benefits are being large enough that it's probably an irreversible trend. The IEEE is a key contributor to the community that is making this shift happen. And for those of you who are IEEE members, I want to thank you for being here, and I want to thank you for what you do. For those of you who are not IEEE members, we like you too. I mean, we are developing communities, not membership. So if you are working with the IEEE members, attending IEEE conferences, publishing IEEE papers, we're happy to have you. We're trying to serve the community, not just members. So thank you all for being here, and thanks for listening, and I'm happy to take any questions. See if I can move out here so you can hear me.
Questions for Bob? We've got right over here. I'll come to you.
Bob, thank you for a great presentation, and it was awesome to listen to you. I'm going to ask a question in a different direction. I have watched the presentation this morning and the other presentations. Like you put it, one of the last slides you had, educators. I think that's an important piece of this whole puzzle. I have been visiting universities and in many of the major ones, and for this whole vision to happen, we are going to be dealing with technology that are intrinsically multidisciplinary. And visiting many of the programs that have been put in place for very major and important universities, they are, I have noticed that the teaching. Oh, can you hear what I'm saying from here?
I'm having real trouble. I can understand about every other word. I'm going to move down. Let me just step down here, and I think that's going to solve the whole problem. I'm going to grab the soundproofs and nuts, but that's okay. Okay, now I can hear you.
So I have noticed that many of the programs that have been taught in large universities, undergrad programs, they are still as it was done before, they are isolated. So power electronics is being taught without involving control systems. So everything is disconnected. So what we have seen today, this morning, and through the other presentations, what all the other panelists have presented, it's clear that these whole systems are going to come from the combinations of multidisciplinary technologies. Can you comment on the behalf of the IEEE or what is happening for this education that you're going to need to be able to build this new future, what's being put in place?
Certainly, and I just want to make it clear that it's a whole lot easier to get the question from here than it is the stage. I understood everything from here. Okay, it's an interesting conundrum that you have raised, because the educational systems have forced, not forced, they have learned that it's important to learn activities in depth. But it's also clear that most modern problems are multidisciplinary. And by multidisciplinary, I don't mean needing people that are an inch deep and a mile wide. By multidisciplinary, it means we need to be able to work together in teams where you know something very intelligent, very deeply, and you know something very deeply, and they're very different, and you learn to talk to each other and work together. And that's really what we're trying to do at the universities now, is to maintain that depth in power electronics or transportation engineering, but to have the people work together on problems and learn to work together to use the skill sets on both sides. I think that's sort of the best answer that we have right now. At least in the U.S., that's the best answer we have. Because you can't teach everybody everything, so what you have to do is teach everybody something and teach them to work together in teams very well.